Hello, it is E.M. Lease, and my camera is working, so that's good. Today we are going to discuss Chapter 2 of Cosmology for the Curious. I've condensed it basically into discussing the Newtonian universe, which is the universe that is governed by larger objects. So this is pre-particle physics or quantum mechanics, whatever you would prefer to call the teeny tiny things that are smaller than atoms. We're going to discuss not only the Newton's laws of motion, his findings on gravity, but also discuss how we view gravity in today's terms based on string theory, which, as I discussed before, basically states that every constituent particle that makes up matter, so quarks, for example, being the smallest known constituents of matter that make up neutrons and protons inside the core of an atom, are actually strings that are coiling around one another and are kind of held together by a membrane called a p-brane, which also aids in housing the dimensions that we are visibly seeing every day, but they curl in, but I won't get into too much of that right now. Basically, these strings possess a vibration that is the signature of that particle, and that vibration governs its tension, its mass, its energy, things such as that. And we're going to look at gravity in the form of a string rather than just as a force, as Newton would have us believe. So here we go, yay! So we're going to go over Newton's first and second and third law of motion. So the first law is that any body that is either at rest or is moving will remain so unless acted upon by another force. So, for example, if I pick up a ball that's at rest and I throw it to a wall, the force acted upon that ball will cause it to go toward that wall, but once it hits the wall, its motion is diverted in another direction, and some of its energy is expelled in the process of colliding with a wall. Second law, if a force acts upon an object, the object will accelerate in its direction of motion, its velocity. So acceleration is when an object that has a speed, the speed picks up, it gets faster. And acceleration is calculated by force over mass, mass being how much the object weighs. Force and acceleration also both have magnitude, so size, greatness, however you want to portray that. Excuse me for Nala, my dog is... Come on, Nala. Seriously? Sorry, my dog is kind of messing around. So force is calculated by mass over second per second, if you want to say second squared. And the reason I annotate my formulas like this is because it kind of helps me get a more a literal understanding of them, as I wasn't really good at math most of my life, and only for the past few years, after really delving in, I've developed these strategies to help me understand it. Nala. Oh, I'm so sorry. Such a cute dog, Nala. So 1 Newton, which is what Newton has calculated to measure these things that he's discovered, is 1 kilogram over seconds per second, or second squared. And in particular, you have to use units, or otherwise your product, whatever sum or calculation you get, isn't really going to be easy to grasp by the less developed mind. And of course, we have something called inertial frames of reference. So it's a term associated with an object that's moving, but not by having a force directly act upon it. And an example of this is the gravitational attraction. So we don't directly interact with gravity. Gravity more so interacts with us by pulling us to Earth, but we're not necessarily being grabbed and thrown around by it. So it's not a force in the same way we would identify force, as we do not directly experience it as interrupting our current motion. It just kind of is. And so force is equal to mass of an object. Force is equal to the gravitational constant times mass of object 1 and mass of object 2 divided by the radius of the distance between them squared. And the gravitational constant, as I've stated here, is actually 6.67 times 10 to the negative 11th power Newton mass squared over kilogram squared. Yeah, that's intense. And you might be wondering why it's negative. And from what I've noted from my reading in all these books is that when it's typically negative, it means that the interaction is so minute that you cannot have it associated with something that is more visibly or tangibly there. So if it's in the negative, it's either really small or the measurement of it is so minimal that it has to go into a negative plane to make sense. So here's the laws of gravity, as Newton states in his books. Gravitational forces are inversely proportional to the square of the distance between two objects. So like think of a circle and a focal point, like its center. That would be an inverse proportion. So you have the radius, the gravitational force between that center and the outer exterior of the circle is inversely proportional to the square of that distance. And this goes in with the shell theorem, saying a uniform spherical shell of matter attracts objects as if the shell's mass were concentrated at its center. So think of this like the moon around the Earth. The moon orbits around the Earth and it is pulled in by its gravity. There is a bit of a gravity push and pull, considering that the moon doesn't plop into us and the Earth doesn't just like go into outer space. There is a gravitational equilibrium. Nala, stop it. Nala, stop it. So a gravitational force exerted on an object that is inside a universe spherical shell of matter is zero. And as I said before with the negative calculation of 10 to the negative 11th power, we're going to say, for the sake of simplicity, as it also states in this book, that our gravitational force is zero. The force we feel is zero, as we're already inside of the sphere and thus are no longer really being compelled toward it, as we are already inside of it. Acceleration and free fall. So a small object is near the surface of the Earth, for example, and it's kind of pulled in. It's going to pick up speed. It's going to pick up momentum, and eventually it's going to free fall into Earth. And the force of that is calculated by the gravitational constant times the mass of the Earth times the mass of the object times the radius of Earth squared. So again, thinking of Earth as a circle with its mass at its center in the dot, and then going outward with a line to the exterior. So that force would be 6.6 times 10 to the negative 11th power Newton mass squared over kilogram squared times mass of Earth times mass of object divided by 6.4 times 10 to the 6th power. Wow. That's a lot. And then we have uniform circular acceleration. So A equals velocity squared over the radius. And again, this kind of goes in with his inverse law. So it's centripetal acceleration. I know this is very boring stuff, but let's get through it. Newton believed that the 1 over r squared inverse law applied and stated planets and other celestial spheres moved in elliptical orbits. Planets generally move within the path of an ellipse, though, as Kepler, who used Platonic solids, calculated as he observed the planet's motion around the sun. So like an ellipse is like a flat circle. I guess it's much more similar to an oval, but the path the planet travels is that at some point during its revolution around the sun, the distance gets closer to the sun and then farther away from the sun, depending on the gravitational push and pull of that orbit. And we're going to look at Venus in particular, and generally quadrivium as it goes into the more cultural adaptation of this. And then, of course, we have velocity, which equals 2 pi r over t, which is 2 times 3.14 radius over time. So time being equal to one revolution of an object around a central object. So the Earth around the sun, for example. And then, of course, we have the macrocosm of the universe, which I'm going to state a little bit about the sun because we do revolve around the sun. Its mass is velocity squared over r divided by g, which is more or less equal to, oh my goodness, I messed up. Darn it, I forgot that number. It's a number times 10 to the 30th kilogram. Nala. Nala, come on, stop being a bad girl. And then, of course, we have energy conservation. There's two kinds of energy, really. We have kinetic energy, which is objects in motion. So K equals 1/2 mv squared. So kinetic energy equals half the mass of a radius squared. Mass velocity squared. Ugh. Potential energy, which is stored energy. I really don't know why they put it as a U. It should be a P in my opinion. So U equals the gravitational constant times mass over radius. And the reason we have the gravitational constant is because it's not in motion, so gravity is indirectly acting upon it to stay where it is. Such as we do not register the feeling of gravity, because since we are already inside of a gravitational sphere, and that's why we have it there in that calculation. Although for us it's 0, for something that has potential energy to move, it is not. And essentially, gravity is affected by that potential energy, as everything has potential to move, gain, and expel energy once put into motion. And Newton, based on these laws of motion and how things moved and how things expelled or retained energy, he concluded that the universe was static and held together by a force of gravity, which must equally affect planetary and celestial bodies, thus keeping everything in perfect alignment. This does not necessarily mean that all celestial bodies have the same gravity, rather that they each possess a gravitational pull unique to their composition. This would mean that, like the moon has less dense gravity. That's mainly because of its atmosphere, its lack of an internal magnetosphere. There's a lot of things that go into determining the gravitational pull of a celestial body, but gravity does affect everything within the universe in its own way. Nonetheless, as we'll see in another review, Hubble discovered that the universe is expanding. So if gravity is attractive, as Newton stated, and was using this fact, as gravity is an attractive force, that everything in the universe is sticking together, why are the farthest regions of the universe migrating away from us? This is kind of the flaw with Newtonian universe, is gravity is only one of 4 or 5, if you count the electroweak force, governing the laws of motion and interaction in the universe. And I mainly use the word interaction because every force does interact with matter and energy differently, but nonetheless, particles do have motion, and particles govern forces. And all forces, with their particle interaction and the way they have their own mass and unique identity, are governed by the Higgs boson field, which I'll go lightly into. It's basically a field of energy that is throughout the entire universe, and it allows for particles to have their mass, and the mass governs their energy, their velocity, where they're going, what they're doing. It basically gives each particle its own unique identity. Otherwise, every particle would just have the same force, same mass, which would be an interesting universe, but sadly that's not the one we live in. So if gravity is a force, it must be derivative of a particle interaction. So gravity could not explain the abysmal differences between the macro universe, one we see in the micro universe, aka the quantum world. Nala, stop it. My dog is so bad. Because if we can see that particles are interacting in a way that is extremely fast, extremely chaotic, as compared to planetary bodies, which more or less move within Newton's calculations. There is this great abyss between what's going on a microscopic level versus that larger level.